so now let's look at the application of quantum mechanics to atoms that have more than one electron. Okay, we've already looked at the hydrogenic atoms, so this time we're going to look at atoms that have more than one electron. So the problem in this case would be you'd have one nucleus and two or more electrons. So what would be the energy that's associated with the center of mass? That's essentially what? What's the center of mass of your atom? The nucleus is where the most of the mass is concentrated. So the energy associated would be up with the center of mass would essentially be the motion of the nucleus, right? And for practical purposes, we can separate that from our problem. That's a separate problem. That will just be a free particle problem. And so we're really more interested in the internal motion, which would be essentially the motion of the electron, so electronic motion. So in the case of helium, the Hamiltonian for the electronic motion will be, what would it be? Our electronic Hamiltonian would be kinetic energy. How many electrons do we have for helium? We have a +2 charge on the nucleus, and you have 2 electrons, right? So I'll call this electron 1, electron 2. So what would it be? Kinetic energy of electron 1 would be negative h bar squared over 2 times mass of the electron times del squared for electron 1 plus kinetic energy operator for electron 2, which would be negative h bar squared over 2 times mass of electron times del 2 squared, where del 2 would be the sum of the second derivatives with respect to x, y, and z of electron 2. What else do we need? So that's your kinetic energy. Potential energy, so plus potential energy of interaction between electron 1 and the nucleus, so 1 over 4 pi epsilon naught times positive 2e is the charge of the nucleus. Charge of the electron is negative e over, let's call that distance r1. So the distance between the nucleus and electron 1, let's call that r1. Only depends on distance. Plus potential energy of attraction between electron 2 and the nucleus. So that would be 1 over 4 pi epsilon naught. Charge of the nucleus is plus 2e. Charge of the electron is negative e divided by the distance between electron 2 and the nucleus. Let's call that R2. What else do we need to add to our Hamiltonian? Interaction between electron 1 and electron 2. So that's 1 over 4 pi epsilon naught negative e times negative e. That's the charge of the 2 electrons, divided by the distance between them, and we're going to call that distance between them R12. Okay? What is R12? It's just what? It's a distance between 2 points in 3 dimensions. Square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So you can see here R12 depends on the coordinates of both the electrons, right? Whereas this R1, this potential energy term, so this one depends on the coordinates of both electrons, whereas these depend only on coordinates of electron 1, right? And these depend only on the coordinates of electron 2. We have our origin set at the nucleus. So if not for this electron-electron repulsion term, this would have been a simple problem to solve, because you have a Hamiltonian operator that's a sum of a term that depends only on electron 1 plus another operator that depends only on electron 2. That you would have had a separable problem. But this problem is not separable because of this electron-electron repulsion term. Okay. Now, from here on, we're going to start using atomic units to make things easier to write, faster to write. So our Hamiltonian, we're going to start writing it as negative 1/2 del 1 squared, okay, plus negative 1/2 del 2 squared, that's kinetic energy for particle 2, plus 1 over R1, I'm sorry, 2 over R1. That's the kinetic and potential energy of interaction between the nucleus and electron 1, plus in this case 2 over R2, plus or minus, oh, negative, right? Minus, let's make that, plus negative 2 over R1 plus negative 2 over R2 plus 1 over R12. Okay, this would be your Hamiltonian, what we would call the atomic units. In these units, what did we do? Basically, what we're saying is we're letting h bar be equal to 1 unit on this scale, on this system of units, and we're taking mass of electron as 1 unit. Okay, so expressing masses in terms of mass of electron, and that would suggest that our unit of charge would be what? Like our E over square root of 4 pi epsilon naught would be 1 unit. Okay, so that would be your atomic units. That would be just a quicker way of writing the Hamiltonian. And in this particular case, our distance would also be, in atomic units, would be 1 Bohr radius. So 1 Bohr radius, A naught in this case would be just 1.